Why is the mass of electrons and protons different? In fact, why is mass variable? Now, in this area, we're going to talk about some main concepts. And concepts in physics and chemistry build upon each other. So you have to understand multiple things. And I know this is complex, but that's what you have to do. So first off, you have to understand the 3D atomic model. That is how electrons fill around a nucleus. And to me, of course, that's the two hemispheres by longitudinal rings or circles. So thereby you get two cylinders. Further, it's important to talk, especially when you're talking about mass, because it's about how forces and acceleration works. So you're talking about the electrostatic and the nucleostatic. And by nucleostatic, I mean the strong nuclear force and the weak nuclear force. The three fundamental forces. Now, in studying all this, the first and main concept will be electrostatic force, which I believe is radial. That means it's the same in every direction and only going out in straight, spherical lines. Okay? Now, I've added for my work as Planck is the main value of that. And it is Planck at the equilibrium. You see, there's one strength that applies to both radial electrostatic and radial nucleostatic. Now they're different, but at one point they have to be equal. And that's the one electron, one proton system. That's a hydrogen atom. And so when you let those two things balance, the push of one, electrostatic, is opposite of the nucleostatic, the strong nuclear. And so I will always be talking about not just Planck's constant, but Planck at equilibrium, Planck at Bohr. And this is done by H hat C. There are free forms depending on what you're at. There's Planck's constant, Planck's hat, and the C is the speed of light. And that is always a system of H hat C at A sub O. And the number is the same for whether you're doing electrostatic force as attractive between electron and protons, or the nucleostatic, the strong nuclear, as repulsive, same value at that distance. So everything you do, but that leads to another thing. What is the maximum strength of fields? Well, for electrostatic, we're going to do here, that's how much is built up at the edge of the particle. It's this much here, but the particle is 1 over distance squared. So it's stronger and stronger and stronger until it has maximum at the edge. And I don't know what happens inside the thing, but I know what it is at the edge. It's a ratio. And so you get this ratio of the Bohr radius, A sub O, and the radius of the electron. This is called something called the fine structure constant. And it's probably the most important ratio there is in subatomic chemistry and understanding bonding and all the things in computational chemistry that we do. However, I think that name is confusing to people. First, it's not a constant. It is a scaling factor. It is how, when you're squared, because it's electrostatic force, those ratios change the strength. Okay? So it's the equilibrium, the Bohr at edge scaling factor. All right? So we will find this ratio, and you'll see it as an alpha. Alpha is the fine structure constant, and it is the square root of A sub O over R sub E. And I will always use these because in most cases, you'll find the field position as relative to A sub O, and this may not change. Now, the most important thing to understand is that then I can take the electrostatic force, this Coulomb's constant times the charge of 1 versus the charge of 2. Oh, sorry, I didn't say 2. Over the radius. This is the potential. Obviously, as a force, it would be over r squared. But I'm trying to then convert that. That really also is some other variable contract called the permutivity of space. And as you go through this, I can substitute for that by this calculation and go through and rearrange these things until you get it to h hat c. That is the strength of Planck at Bohr at the h hat c version times the number of particles. I don't have that concept of charge. I have the concept of only Planck. The number of charges in this 1 and the 2. I did it properly there. Good. All right. And this exchange ratio, that scaling factor. And so this is understanding of charge. Charge is a position within a field. At the Bohr radius, it's this strength. Okay, and then there's a graph. It's a 1 over distance cubed graph. It gets weaker as it goes out. Okay, and then, so it's stronger here at the edge. And all you're doing is you're doing those two. And almost all calculations will be done at one of those two positions for now. Either the Bohr radius or the particle edge. And by doing the ratio in this manner, if you're out here at the particle edge, if you're at the Bohr radius, those eliminate. If you're here, okay? And so this is how electrostatic charge is a position in a field related directly to the Planck constant. Now, unfortunately, this is a little more complicated because we do this scaling factor and we're trying to put into these two fields, electrostatic and nucleostatic, and also we've gone since the time of Newton with Newton's second law. Acceleration equals force times mass. Now, when you work with me, we're actually can eliminate mass, just like I just did for charge. So what happens in charge is that in part, I want that scaling factor at the potential level to scale directly with this. And that leaves an extra 1 over r a sub o over r sub e to that 1/2 power. So, and this is the scaling factor. So every equation that you do in the field acceleration physics stack is based upon strength constant, counts, number of particles, quantization, which will become even more important when you get to statistical mechanics or what they call quantum theory. And then you're going to have that distance scaling because that's how you're going to change where you are relative to that constant. So your distance is not just meters, which is an arbitrary length, but the length of in the count of units that the fields universally in the universe change at. But then you have this two field. And that's the net actually of the two, which I'll explain next. You see, we have electrostatic force and we have nucleostatic force, the strong and the weak. And the two radials are the strong and the electrostatic. As a potential, which is where I did the equation because that's where the famous physicists do, there's also force, potential and force. This is what everybody's been taught about. And then force also happens to have the same, is just divided by 1 over mass, divided by mass, to get you acceleration and field. And while for the last 100 years, they've concentrated on potential and force, my work concentrates on acceleration and field, and thereby eliminates some of these things that we have to do in statistical mechanics and eases some of these equations. First, by separating the things so I have the right frame of reference, and 2, eliminating those things that are not yet at the level of being a statistical equation. So The important thing for here is that potential is 1 over r for electrostatic. Acceleration is 1 over r squared. We know that from the Coulomb constant, okay? And the same would apply if you divide that by mass, okay? It still is going to be a 1 over r. And the field is 1 over r cubed. And of course, that sort of makes sense for a radial force, because the radial force, the volume of it will be 4/3 times pi r cubed. Pi r cubed, oh, guess what? So that force here is spread out over that entire volume, okay? And so that's why fields, and that's part of how I'm going to make things simpler and easier to understand by applying position within a field to understand mass. Now, the nucleostatic also has this schedule. In fact, there's something called the Coulomb constant, which is in this format, epsilon to the minus alpha mu r over r. And this comes from Euler hundreds of years ago, and basically is the description of a statistical mechanics equation. But the thing is, he used actually a different mu, and the current mu is a pi meson, and that is actually value is somewhat close to 1 over r. So I get down to e over 1 of r, which, if you know the equation of statistical mechanics down here, the integral of it is 1 over whatever that is to itself. So it's a very simple transition. You actually only have to end up with this 1 over b. So that r actually comes down and becomes r squared. Wait, so that means this is r squared, r cubed, and r to the 4th. And this is actually was discovered, but wrongly attributed by Bohr himself. He called it 1 over r, but he thought it was a gravitational orbit, like the planets going around the star, or stars, and that does use 1 over r, and that volume is the extra push out that balances the pull in. But this is not a rotational orbit. He used the words orbital and angular momentum based upon that physical model. Now, Bohr is correct, the math is correct, but the name is wrong. It is not a rotational orbit, but it is an extra 1 over r. And I will call it that very often to remind you that you're at that second layer, but I call that static. That is not a rotational order. It's to remind you that it's just that. Now, this is offset by the weak, and that's beyond this class. Now, the transition between these two then gets these scaling factors. You see, you have to move from a 1 over r squared to a 1 over r cubed. And that actually uses that ratio at the 3 over 2. And remember what I said, that alpha over that equals 1 over that, oh, needed a square there, over that square. So now you can calculate this, and if you're going in the field level, you're going between r cubed and r 4th, so it's a sub o over 4 over 3. But if you're going the other direction from nucleostatic to here, it's 3/4, depending on which you're going. You will see this a sub o over r sub b time to an n power, and that power will depend on whether you're electrostatic, nucleostatic, whether you're a transition between the two, and which direction it's going. In fact, we saw that a little earlier because I said that was a net 2 force. You had this minus the ratio that was used for just 1, and that minus 1 becomes the 1. And you can actually see that here. That is the net 2 field in the current electrostatic equation in my version. And you'll find these 1/2, 3/2, 2/2, these various ratios throughout. But now you can look at those and say, I know what they physically are. I know the direction and I know how they are within the field. And that's going to be important in determining the mass, one of the most complex concepts in all of physics. So let's move forward. Now that I have that scaling factor, how does that apply? It should be easy. We've had charge, and I showed that the charge, if you take square of that ratio, that's the difference between Planck and charge. And charge is a very simple concept, and whether you get a positive charge or a negative charge, they're the same amount, and that same even scaling going from the Bohr radius to stronger at the at particle edge. Okay, so here's the actual calculation. We're calculating at R sub E and A sub O. There's those two calculations using Coulomb, and the difference is a ratio of 352,000, and that is R sub E over R squared, which is 1878. That's the direct ratio here. Squared is also that same number. Okay, that's the electrostatic. Now let's get to the tough part. Let's look at that same scales for the mass field. Okay, so everything that we're doing, we're trying to put into electrostatic forces because that's what we've done. So as I said, every time we're doing it, we're trying to, all the equations that we've done for the last 100 years have been using this field. And then they'll throw in these calculations to sort of pseudo make all of these into those. So if you take the ratio of the distances, okay, obviously that's 1 to 1878, okay, but for the squared, okay, which is, you'll get this number, and that number there is what's called the fine structure constant, and what I call the root of equilibrium versus edge, or Bohr versus edge scaling factor. Now, cube versus cubed, well, that's electrostatic to electrostatic. Obviously, I haven't seen very many equations because it's already, both sides then are probably in the same unison, same place on the physics stack, okay? However, when we get to this field, that counter of that field is a to the fourth position, which is 142 trillion, million, billion, trillion. That's a huge number. And that's versus this number. And what's really funny is that that is 1643, 1604.2. Now, that's not a number that we know. Well, that's right, but it is 1878 to the 3/4 is this number. And that is what happens if you have a proton mass and you've moved it down to the Bohr radius. Okay, but that's not the ratio that we need. Let me explain that. You see, the system of the world comes in 3D. Okay, that is the correct mass of a hydrogen if you just had an hydrogen all by itself. But hydrogen is so reactive, I've, in my chemical analysis, hardly ever find that. Instead, what we always find is Pauli pairs, and I call them Pauli hemisphere pairs. You see, you have the electrostatic attraction up to that Bohr radius, and at that point, that repulsion is 1 over distance, electrostatic 1 over distance squared, 1 over distance cubed. That becomes a wall of repulsion. So all the electrons want to come into the Bohr radius, and then bang, they hit this exponentially stronger repulsion. Now, that's fine, but whenever you get 2 of them, these 2 electrostatics, okay, they're the same type, so they do not express nucleostatic. Nucleostatic is only expressed where one of the particles is a color particle, and there is a change in the strength. In other words, a plus and a plus wouldn't do that. A minus and a minus would not do that. So that leaves them with only electrostatic. They want to be as far away from each other as possible. So this is probably very confusing for young students because you get things like a Lewis diagram in chemistry where they put two pairs on four boxes, okay, around the boxes to explain bonding. And that's not what happens at all. It's in 3D. Those two pairs in a Lewis diagram are at 180 degrees, as far away from each other as possible, but still net attracted up to the Bohr radius to each other. But the math doesn't bring them to the Bohr radius because you've still got the two of them there pushing each other apart. And that's what I'm going to explain here. You see, the distance is 1 over distance squared, but you've got this other one at 2D, and it's missing the electrostatic. So I'm just going to work at the 1 over distance cubed radial nucleostatic force, the strong nuclear force applicable electron nucleon. And so there, you've got distance cubed times 2 over distance cubed equals 1 squared here and 2 squared here. So it's 1 minus 1/8 or 7/8. Okay, but if you do that, if they're pushing each other and one is reduced by 7/8, the distance is going to result in that flipping to 8/7. So that will make the electrons in a two-cylinder not be at the Bohr radius, they'll be at the Bohr radius times 8/7. And of course, this is adjusted for the number of nucleons. Obviously, a big uranium is much bigger and has much more force. But let's just do that as if it were simple. So let's go back to, if I've gone the ratio for going from a proton at the center of the system to the Bohr radius is 1604. If I multiply that by 8/7, I get 1 over 1833.2. That would be a stable hydrogen that never touches anything else, okay? Or a stable two electron helium. But in every other molecule, and in hydrogens and heliums, if they are part of those systems, the relationship has to add one more thing. And that's because those particles actually have radius. I can't do everything as a point equation. The nucleostatic actually builds up another R sub E. And a famous set of work by Schwinger, Feynman, and Tokunaga determined that additional amount to calculate because it's not a point equation. Those things actually have physical dimensions. Now, they actually didn't describe it that way, but that's my interpretation. And that's called the anomalous moment. And its value is 0.0011589, and it keeps going. And again, we're translating it between its nucleostatic versus electrostatic. And when you do that, that becomes 1836.16. And the experimental value of the mass of a proton versus the mass of electron is 1836.153. Very, very close to what I've done, using the position within the field in the field acceleration physics stack without mass. This is based upon number of particles for complete two-cylinder systems. That means you must have at least a molecules bigger that have all of the subshells. You have to have a p subshell for this to start. So what is that 1 over m, and why does it vary? Okay, I've explained the ratio between protons and neutrons based upon position within a field, but why is that field important? Now, I'd like to think of this. If you have an equation and you have a spaceship and it's moving in this direction, there's no resistance. And so you just calculate those point equations for it. However, if I have boats and one has a keel that's very, very trim and another one has a big bulk that goes down, even if they're the same weight, this one, and they're moving this direction to the left, this one goes slower because the profile of that resistance is bigger, okay? And ships do this often because they want to not tip over and they want to have the weight very much down here at the bottom. That distance going down here is what I think of as the slow. If it was a spaceship, it would accelerate really fast in vacuum. But if you're a boat in the water, you have to calculate the energy to get this mass moving divided by the resistance. That is what Newton's A equals F over m. Acceleration equals force over mass. That means whenever I see the two, I can calculate the acceleration, but I can always then take that calculated acceleration and divide by the resistance, and now I can calculate that resistance, and I never have to have variable mass or force in equations. That's the secret of the field acceleration physics stack. Now, there's some more things to measure. Obviously, when you're in ships, waves do matter. If these are going up and down, that actually changes this calculation, makes it more difficult. Well, the same thing happens in physics. The other thing is that the depth is not critical. It's really about where it is relative to the other ships. And that's something that we'll get into deeply later in relativity. So I think of this ocean of other fields out there, okay, being about the distance of where that body is versus the fields around it, okay, being the amount of resistance to any acceleration. So we can calculate the acceleration of electrostatic as a vector. We can accelerate the acceleration of that, but we always have to decide that these particles are in the field and they have to move that whole field, which means they always have this resistance to actual movement in those situations. And those resistances are not at squared or cubed, they're at the cubed and to the fourth power, thereby getting that 3 over 4 in the variance of their strengths. So this thing is that all of the fields are an ether, an ocean of fields, which are subject to wave functions and are subject to relativity. And as such, you can calculate the accelerations in clean point equations, but understanding that there is a counterforce because you have to move those within a counter fields out there of other items that may or may not have waves that you'll also have to count on. And this is part of developing the field acceleration stack instead of the complex mass, which is variable, which is different between protons and electrons and even neutrons, and which becomes arbitrary. So we fix something and we get a great force equation, but then we put it through another manipulation, which may or may not have fixed this. So we have all these wonderful things that we've done, and then we mess it up before we actually get to the physical attributes. The way we want to end up is with position, velocity, acceleration, and fields. A clean math and physics stack that explains everything. And it explains variable mass and why, by the position within that field, as a counterforce, replacing Newton's second law for why an electron and proton have different masses at different ratios, and what those mean in terms of expanding and simplifying the equations into separate parts where you can understand what the mass is specifically instead of making it variable. Now, why then is mass why did Newton think it was the same? Well, one is he wasn't there when we figured out subatomics. And for him, mass was just a number and it worked great. That counterforce was consistent. But let me explain to you why it isn't consistent. You see, those two fields that you're trying to do is the electrostatic, which I show in red, and the nucleostatic, which I show in green, and it is the sum of them. Now, this is the Bohr radius where they're both the same. I know their signs are opposite, but when you're trying to do resistance, it's distance, it's the absolute value because it's the distance of that field that you're being pulled away from equilibrium. And so both of them operate as both positive. In my other graph, you'll see those as positive and negative going to a net, which of course makes the accelerations the same. A sub O, Bohr radius, electrostatic, nucleostatic equal. However, and here you can see there's that wall of repulsion, okay? But what you see is that the sum of those, because 1 over distance to the fourth gets smaller, faster, exponentially faster, that once you go out 1 Bohr, 2 Bohr, 3 Bohrs, 5 Bohrs, 5 Bohrs, you're probably the size of most atoms, okay, with all the shells and then some bonding distance by the time you're out at 4 times A sub O or 5 sub O. That electrostatic is almost exactly like the field resistance. And so beyond this distance, for 100 years, or even for 100 years, certainly, they've just calculated the resistance as the electrostatic field at 1 over distance cubed and forgotten about this piece. Well, they didn't forget about it. They just started making all sorts of abstract calculations for what is variable mass. But when you do it this way and you actually use the variance as the sum of those two fields as a resistance to whatever point equations you've done for acceleration, you actually know why mass is changing, why mass is not the electrostatic. Here's the electrostatic field, but the resistance is higher. And the resistance, of course, by the time you cross the Bohr radius, nucleostatic is actually more important than electrostatic. And this number becomes 2x, 3x, and at the Bohr, and you can actually calculate the maximum of that, which is Einstein's E equals mc squared. Thank you.